Swayam Prabha. Digital India. Educated India.
Good morning, good afternoon, good evening, my dear friends. I am Raghunandan Sengupta from the IME department, IIT Kanpur, and this is the Total Quality Management 1 course under the NPTEL MOOC program. And we are continuing our discussion about the moving range charts corresponding to the fact that whether normality holds or normality does not hold, and this is the 27th lecture depending on the discussion which we have just finished in the 26th lecture. So, consider an example for this discussion which you already had. So, 1 pound coffee cans are filled by a machine. So, they are a process, not a production process. They are sealed and then when weighed automatically. So, production process, I do not mean like manufacturing a tie rod or trying to basically manufacturing electrical equipment, but they are just filling up bottles. After adjusting for the weight of the can, any package that weighs less than 16 ounce is cut out of the conveyor and removed. The weights of 25 successive cans are shown, and they are shown in the figures are shown in 6E19, which is the table on the right hand side when I am pointing my right hand. We are to set up a moving range control charts and a control charts for the individuals. Estimate is required for the mean and standard deviation of the amount of coffee which is packed in. So, we want to basically give our opinion whether it is reasonable to assume that the can weight is normally distributed. So, the can numbers are given in the first column, in the third column starting from 1 to 25. The weights are given from the first can is 16.11 till the last one which is 16.10. So, obviously there are different type of variations also. So, we basically write on the R code. You basically save it in a matrix. The matrix is basically of size 25 cross 3. So, it will basically with the serial number, the can and the weights accordingly. So, the data if you call basically the weights are given starting from 16.11 to 16.10, and we want to basically plot the moving range charts. So, the moving range charts would be basically calculated by finding out the mod of the difference. So, if I concentrate on the first two readings, it will be 16.11 minus 16.008. So, that would be mod, and for the last value obviously it will be 16.13 minus 16.10. Again you try to find out the mod of the weights. The charts when you draw, obviously you will try to find out the average, the upper control, lower control and corresponding to that, and then based on that you have to basically give our judgment whether it is normal or not. So, we should keep in mind in the chart the control limits are rounded off according. So, they can be either put to 2 places or decimal, 3 places or decimal, but we are trying to round off to basically give a fast result and do the calculation, but that would not matter, conceptually would not matter whatever we are giving. So, if you basically give the values, so your upper control, lower control and the central line all are given as 16, but they are not 16. Obviously, in order to make it understand in the graph, I have given the values of central values as 16 point something, upper control 16 point something, lower control 16 point something. So, if you find out the moving ranges, so this value which you have, the value which you have here or here or here or here or here are basically the difference of, so this is x minus 1 mod of that. So, the moving range is given by this mod of this, and we do the calculations accordingly. So, that is why it is not negative. So, once you do the calculation, Then you do the data concept for the finding out the range, the difference of the range, and do the calculations. So the ranges are given in this way. The central line is 0.024 based on the calculation of the central line. The upper control values is given by 0.078 and the lower control value is given by 0. So obviously you have the overall charts for each and every moving range values are like this. So you not to basically need to comment about intelligently about the normality. So the mean value is about 16.052, which if you remember I didn't mention. Obviously I know that a more explicit drawing of the diagram would definitely be much more exciting, but I want to give you a feel that how you can do that using the actual information which is there in either in the book or in the actual processes which can be available, and then obviously you will try to utilize some of the concepts of R. Now if you remember I did mention that we are trying to utilize R in our work. So here the value comes out to be 16.052. The standard deviation comes out to be, say for example 0.8865 multiplied by the mean value of the range. So mean value of the ranges are basically the mod of first reading would be mod of the difference of x2 minus x1 mod of that, second would be x3 minus x2 mod of that, add up all these values, divide by the number of readings, obviously that will give you the average, which is, if you look in this chart, it is about 0.02375. So multiplying that with the value of 0.8865, it comes out to be about 0.0210. So once we do that the plotting of the graph, you will basically find out the upper control, lower control. Now if you remember where we had closed the discussion in the last lecture, it was mentioned very explicitly that you need to do basically the finding out the QQ plots or some plots corresponding to the distribution and to find out whether it's normal. So one of the very good plots where you can find out where the distribution what type of distribution is basically the QQ plot, which is the quantile plot. So I'll come to that later on with discussions. So if you do the quantile plots, the quantile plots for the information set or based on the range values and the mean values for filling up the coffees are given in the diagram which is there in front of you in the slide. Now here I will pause to give you a concept about what do we mean by quantile plot. So I will try to basically explain it using the words, and I will repeat it slowly so you will understand. Now consider there are two distributions, and this quantile plot is very intuitive method by which you can understand what type of distributions actually is, and you can make some actual very nice, intelligent and very simple judgment based on the information which you get from the quantile plot. Quantile plot is basically to do with two different distributions. What are the distributions? I will come to that later. Based on the overall coverage of the probabilities of the quantiles. So if I cover 10%, so corresponding to the 10% coverage of the total set of values which is there for the overall observations, I should have covered some overall probability. So obviously remember the probability for the overall coverage is 1. That means when I draw the CDF value, the overall coverage of the area under the cumulative distribution function or the distribution function is 1. Now consider there are two different distributions. For the time being, consider both of them are normal, and the number of readings are different, and they are being taken from two different normal distributions. So what I do is that I basically take the first normal distribution, rank it from the minimum to the maximum, do the same thing for the second distribution which is also normal from minimum to maximum. Now what I do is that I cover a certain quantile range for the first case and certain quantile range or some number of observation for the second case. Now as it is normal, the overall coverage which is happening at a certain rate for the quantiles would be of equal values technically in the theoretical run. So, if I basically covered half of the set of values for the first and the second, the overall coverage of the probability would be 0.5 in the both the cases. If I have been able to consider, say for example 25 of the area, then obviously the number of readings which are there for the first distribution and the second distribution, considering both are normal, would also be the same. Now, if I intuitively plot it on an xy scale, where along the x direction I am plotting, say for example normal distribution 1, whatever the mean, whatever the standard deviation is, and along, say for example the y distribution I basically draw the second normal distribution, whatever the mean distribution, whatever the variance is, that is immaterial. So, if I am basically able to fit a 45 degrees line in those y and x axis, it would mean the quantile plots or the range of coverage, range not the overall area, range of coverage of both the set of values which are normal would be such that the set of points would always be along this 45 degrees line. Now, think intuitively, if I am trying to basically draw, so sorry, this is not the way I should basically do. This is 45 degrees. This is the quantile for distribution function 1. This is distribution function 2. So, if I am on this line, always on this 45 degrees line, it means that the overall coverage which is happening both for the distribution are proceeding at the equal rate and they are covering the equal area, which means that underlying the distributions are same. Now, along the fact, if I replace one of the distribution as normal and another distribution in whatever data which I am getting, and if both the quantile for the normal distribution which I know and for the other distribution which I do not know match, which means that I can convincingly say that the actual distribution which I am tracking and trying to fit and trying to plot against the normal distribution is also normal. So, now obviously you will ask that why normal distribution, can't it be any other distribution along the x axis? The answer is yes. Say for example, I am taking the, technically I am taking the exponential distribution, theoretical exponential distribution along the x axis and trying to basically take another distribution from nature or from some reading and trying to plot the distribution function of that unknown distribution along the y axis. Now, if the quantile plots for both of them happen along the 45 degrees line, then obviously we are much more convinced that the actual distribution based on which we are trying to study and trying to compare with a known exponential distribution is also exponential, whatever its mean and variance be. Now, when I am trying to do that study for different type of distribution, the main focus basically becomes that let me try to understand the QQ plots for the quantile plots for the unknown distribution based on the fact that the known distribution which I am trying to plot along the x axis is normal. So, if you basically find out that the normal quantile plots is as shown in this slide in front of you, you will just note down what are the x and y axis. The x axis basically gives you theoretical quantiles which I am trying to cover for a theoretical distribution, and the y axis basically gives me the sample quantiles based on the readings which I am just taking. So, if the fit is 45 degrees line, it means the reading from where I am trying to plot is basically a type of distribution which exactly matches the theoretical distribution. And now, if the theoretical distribution is normal, then the sample observation which I am trying to take and trying to study is also normal, whatever the mean, whatever the standard deviations be. So, few of the references are, you can basically understand the QQ plots from, as I mentioned that before the starting of this course, there are very good data sets either in Carnegie Mellon or University of Florida. So, one such very good source apart from these two universities is Virginia University, and basically you can have a look at this information set for the library functions, or the data from the library can be utilized for trying to understand the QQ plots. Now, having discussed at length for about 2-3 lectures or more than 2-3 lectures about the variability charts based on the random variables, we will try to basically discuss maybe to that extent the concept of attribute charts. So, consider that attributes are the characteristics which I did mention. So, consider a glass container for a liquid product We examine the container and classify it into one of the two categories, which are basically considering conforming and non-conforming based on the attributes of the characteristics. So, which depends on whether the container meets the requirements, whatever the requirements, may be color, may be shape, may be the crushing power. Like say for example, I want to manufacture some cans, and the cans after usage should be crushed very easily such that they cannot be reused. So, obviously my main focus would be from the point of view the attributes would be how easily they are crushed. So, depending on, and let me continue here, that depending on whether the container meets the requirement on one or more quality or quality characteristics. So, this is an example of the attribute data. Attribute charts are generally not as informative as variable charts because there is typically more information in the numerical values. So, numerical values gives you actual and understanding that how you are trying to measure it, and these readings would give you an actual feel that how you are going to analyze. But characteristics would be a little bit subjective. I am not saying that you are losing in information, you have to basically do a lot more understanding of the attribute characteristics. So, they would be subjective, and based on the subjectivity you have to basically do your analysis accordingly. So, attribute charts are generally not as informative as variable charts because there is typically more information in a numerical measurement. Attribute charts are particularly useful in service industries and in non-manufacturing quality improvement efforts where they are important, they would be utilized. Control charts of fraction non-conforming, which is the P charts. So, there I will consider the conformity and non-conformity for the attributes which I are trying to study. The fraction non-conforming is defined as the ratio of the number of non-conforming items in a population to the total number of items in that population. So, you want to find out the fraction or the chance or the relative frequency, which in the long run is basically the probability. More you do, more it basically tends to a certain value, which is the probability. Like tossing a coin, I find out the head and the tail for 100. So, in heads is 45. So, the actual relative frequency is 0.45. Again I do it, I find out it is 47. So, relative frequency is 47, 0.47. Then again I do it, I find out the numbers out of 100, say for example 55. So, relative frequency is 0.55. So, if you keep doing it, the average basically in the long run it basically becomes exactly equal to 0.5. So, continuing the discussion, the fraction of non-conforming is defined as the ratio of the number of non-conforming items in a population to the total number of items in that population. Of multiple quality characteristics, even if one is not met, the item is said to be non-conforming, and obviously we take actions accordingly. Sometimes fraction conforming is also studied, and we get a control charts on the process yield, and then we can pass some intelligent judgment about that. So, statistical principle on our fraction non-conforming would be basic underlying distribution would be binomial. Why binomial? That would be either yes, no, good, bad. So, basically we are passing judgments based on the outcome. So, let P be the probability that a unit will conform to the characteristics, or 1 minus P would be the probability that the unit does not meet the characteristics. It can be extended to the multi-variate case also, like it can be probabilities of P1, P2, and another third would be 1 minus P2, P1 plus P2. So, obviously it would be multinomial distributions accordingly. So, let me read it again. Let P be the probability that a unit will not conform to the specifications, and all units produced are independent of each other. So, obviously it will mean that the Bernoulli trial characteristics would hold true, which means that each trial, in this case for a binomial case, there would be two outcomes with probabilities P and Q, where the sum of P plus Q is 1, point number 1, which I mentioned. Point number 2 would be the corresponding probabilities of P and Q does not change from trial to trial, point 2, and point number 3 is that the probabilities are independent of each other. So, if I am tossing a coin, the probability of getting a head for that particular coin, if it is an unbiased coin, remains as 50% throughout the experiment, and the probability of getting a head would not affect what is the probability of getting a head in the next trial or getting in the trial in the next trial. So, it basically it is independent from trial to trial, and this would be the concept of Bernoulli trials. So, again reading it, all units produced are independent. If a random sample of n units is drawn and D is the number of defective items, then D would basically follow a binomial distribution with the corresponding P PMF, because PMF is probability mass function, would be NCX. So, this value which I am seeing here in front of me, which is Nx, is technically is equal to NCX, the number of combinations of taking x from n number of observations. P to the power x 1 minus p to the power n minus x. So, obviously, you have n number of chairs to be filled up, x are of one type, n minus x are of other type. So, the overall combination becomes NCX. And now, for each filling up of one chair of type P or probability P, obviously how many such P's are there? It will be x. So, hence it is p to the power x, and the rest of the spaces are filled by the opposite type, which is 1 minus p, which is q, and that would be raised to the power n minus x, because those are the number of places it can fill. So, if I want to find out the fraction of the non-conforming, which is actually p in the long run, that should be basically d by total number of sample size. So, more number of observations I pick up, n increases, d in the long run would be such that the ratio of n by d in the infinite case, when I am taking actually the overall population, should be exactly equal to p. So, when p is known, the proportions of defects or non-defects are known, the upper control limit and the lower control limits are given by, upper control limit is given by p, plus this 3 value is again coming from the overall variability of plus minus 3 sigma. So, this is 3 in the upper control limit, 3 in the lower control limit, are those facts are taken into consideration that I am trying to find out, plus minus 3 sigma accordingly. Now, what is important to note in this calculation is this. Now, if you remember, for the binomial distribution, the mean and the variances would be calculated in such a way that if I try to find out for the corresponding sample, the sample, wait, let it be open, the sample corresponding variance would be given by PQ by n square. So, if I draw simile with the normal case, what I had was basically sigma square by n. So, this would be, wait, let me write it again, because so when I am trying to find out the standard deviation, so it will be square root of that, which is sigma by square root n. When I want to find out the standard deviation, it becomes this, which is p into q, which is p into 1 minus p divided by n. So, that would be basically be the overall dispersion quantum. So, per unit quantum of dispersion onto the left, the right. Now, what is the coefficient which you are going to multiply with that dispersion quantum would basically depend on what is your level of confidence which you want to have. So, again coming back, this 3 value or 2 value or 1 value would depend that whether you are trying to find out some concept relating to plus minus 6 sigma, plus minus, I am sorry, it would be 6 sigma, which is plus minus 3 sigma, or it would be 4 sigma, which is plus minus 2 sigma, or it is 2 sigma, which is basically plus minus 1 sigma. So, based on that, the calculation which are shown in front of you would make sense. So, when p is not given, what we do is that we first try to find out the best estimate of p, which is given by p hat, which technically would be the ratio of d to the sample size. And once we find out different type of such estimate, we need to find out what is the average. So, that average of p hat or p bar would be utilized for all our calculations correspondingly. So, as mentioned here, the p hat would basically be, so now consider that you have taken n observations the first time. So, the p hat would be p hat 1, that means for the first set of observations. Then I take another set of observation, which is the second one, again n number of times. So, then I will find out the p hat for the second set of observations would be p hat 2. If I continue doing it, say for example, if I have m number of them, then the average would basically be the sum of all the ratios of d by let me write it down, it will be easy for me to explain. So, basically I have p hat 1, p hat 2, so on and so forth, p hat m, and average of that is basically what is given here, which is sum of all the ratios of p hats I is equal to 1 to n, find out the sum and basically divide by the number of observation which is there, which is m, number of observations corresponding to the number of samples. So, in each group we have n, and how many such n's we take, which is m. So, then we will basically replace very simply the p's with their p hats, which basically the average values which you have taken. So, initially which you had is p plus minus 3 p into q divided by n square root. So, these p's get replaced by p hat, these q's get replaced by 1 by p hat, this p gets replaced by p hat. P hat means p bar, the average of this p hats combined m number of times. So, finally, we calculate the limits of the upper control and the lower control and find out the central line. So, limits calculated from initial sample should be treated as trial control values, and we will utilize them for trying to basically draw the control limits. Usually some target values of p is given from the tables, based on that we do our calculations accordingly. So, let us consider an example. Frozen orange juice concentrates are packed in 6 ounce cardboard cans. These cans are formed on a machine by spinning them from the cardboard stock and attaching a metal panel. So, basically you are spinning them, trying to make out from the cardboard and putting the cap accordingly. By inspection of a can, we determine whether when filled it could possibly leak on the side or the seam and around the bottom. So, the numbers are given on the first column, the cans, how many such cans are done, how many defectives are given, which is 12, 15, 8, so on and so forth, and the non-conforming ratios are given. So, I find out the ratio 0.424, 0.30, so on and so forth. I find out the p bar value, which is from the overall average of 347. So, based on that I have p bar, I find out 1 minus p bar, I have the n, and I do the calculations accordingly to find out what is the upper control, lower control and the central value. Based on that I draw the charts. I will continue that in the 28th and the other lectures, and I wish you all the best and thank you very much for your attention. Have a nice day.